All right, today we are diving headfirst into one of the biggest, deepest mysteries in all of science: what quantum mechanics actually means. This is a story full of mind-bending paradoxes, and really, it's a battle for the soul of reality itself.
I mean, here's the thing. Quantum mechanics is ridiculously successful. The accuracy of its predictions about atoms and particles is just staggering. It's the bedrock of everything from your smartphone to an MRI machine. But the moment you ask what it's all about, what it's telling us about the world, the answers get really, really weird.
And hey, if you're already feeling a little lost, you are in excellent company. The author of our source material, the physicist Jim Baggott, said he felt the exact same way even after getting his doctorate in the subject. He knew how to use the theory, how to do the math, but he was just floored when he discovered these deep philosophical battles that were raging underneath it all.
So, to help us get a handle on all this, Baggott frames the whole debate as a game of theories. And let's be clear, this isn't a game about who's better at the math. Pretty much everyone agrees on the equations. Note, this is a much bigger game. It's a high-stakes contest to decide what reality is. Now, before we can meet the players, we have to know the rules of the game. And these aren't just suggestions. These are 3 unbreakable, experimentally proven facts about how our universe works. Any theory, any interpretation has to play by these rules. No exceptions. Okay, rule number 1. Nature is lumpy. Down at the smallest scales, things don't flow smoothly. Everything comes in these little distinct packets, or quanta. Think about an electron in an atom. It can't just gently slide from one energy level to another. Nope, it has to make an instantaneous quantum jump. It's here, then it's there. There's no in-between. Rule 2. This one starts out pretty normal. Sometimes quantum objects act exactly like you'd think they should. You take an electron, for instance, and it can behave like a tiny solid ball, leaving a nice, clean track in a cloud chamber. You know, it's either here or it's there. Simple enough, right?
Well, here's the twist. That exact same electron, if you set up the experiment differently, completely stops acting like a particle. Instead, it behaves like a spread-out wave. It can actually pass through 2 different slits at the same time and interfere with itself, creating this classic pattern of bright and dark stripes, just like a wave of light or water would.
So, what do you call this bizarre behavior? It has a name: wave-particle duality. A quantum object isn't just a particle, and it isn't just a wave. It's somehow both at the same time. And that is the second unbreakable rule of our game. And that brings us to our third and final rule, courtesy of Heisenberg's uncertainty principle. And the key thing to get here is that this isn't about having clumsy measurement tools. It's a fundamental law of nature. It's like reality itself has this built-in fuzziness. The more you try to pin down where a particle is, the less you can possibly know about where it's going.
Okay, so those are the rules: quantization, duality, and uncertainty. Every theory has to follow them. So if everyone agrees on the rules, what are they even arguing about? Well, it all boils down to a really deep philosophical choice about what the word reality even means. I want to be super clear here. The fight isn't about the equations or the data. The players in this game all agree on the predictions the theory makes. The conflict is about what we're supposed to demand from a theory. Is it just a tool that helps us predict stuff, or should it be painting us a true, honest picture of the world? Baggott uses this brilliant metaphor to explain this whole thing: the ship of science that's sailing between 2 different shores. On one shore, you've got metaphysical reality. That's all of our deep-seated assumptions about how the world should work. And on the other shore is empirical reality, the cold, hard data we get from our experiments. The whole process of science is basically sailing your ship from the shore of your assumptions, building a theory, and then sailing it over to the other shore to see if it crashes against the rocks of the facts. And you just keep sailing back and forth, refining your ideas. The game of theories is really about which of those 2 shores you think is more important.
All right, now that we've got the rules and we know the layout of the playing field, it is time to meet the teams. We're going to focus on the 3 heavy hitters in this game, and each one has a totally different way of looking at reality. So here's our lineup. First, you've got Team Copenhagen, the old guard. They say the theory is fine, just leave it alone. Then there's Team Hidden Variables, with Einstein as their champion, arguing that the theory is missing a piece of the puzzle. And finally, Team Many-Worlds, the wild, radical contender that says, hey, what if every single possibility actually happens? Let's start with Team Copenhagen, the traditional powerhouse. Their famous, or maybe infamous, motto is "shut up and calculate." Their whole point of view is super pragmatic.
The theory is a tool, and it's a tool that works flawlessly to give us the right answers, so don't get hung up on what it all means, just use it, do the math.
So what is an electron doing when we aren't looking at it? The physicist John Wheeler came up with the perfect metaphor for this. He said it's like a great smoky dragon. We can see its tail when we set up our experiment, and we can see its head pop out when we get a result. But its body, the part in the middle, that's just a big cloud of unknowable quantum fog. Don't even bother asking. Now, Albert Einstein absolutely hated this idea. To him, all the randomness and the uncertainty in quantum mechanics felt wrong. It felt incomplete. It had to be a sign of our own ignorance, not some deep feature of reality. His famous line, "God does not play dice," became the rallying cry for team hidden variables. They were convinced there had to be some deeper, unseen factors that were secretly pulling the strings. For decades, this was just a philosophical food fight. But then a physicist named John Bell came along and changed everything. He devised an actual mathematical test. His theorem proved you could experimentally check if reality was both local, meaning no spooky action at a distance, and realist, meaning things have definite properties before you look. The experiments were run, and the results were a bombshell. Our common sense view of the universe, Einstein's view, it failed the test. One of those two assumptions had to be wrong. Einstein's hope for a simple, hidden reality was out. So, with Einstein's view in serious trouble, a much, much wilder idea started to gain ground. Team Many-Worlds just takes the theory completely at its word. They say the wave function, the thing that describes all the possibilities, is real, and it never collapses into just one outcome. Instead, every single time a quantum measurement is made, the entire universe branches into separate parallel worlds for every single possible outcome. And this leads to some truly bizarre, kind of unsettling conclusions. Take the quantum suicide thought experiment. Imagine a gun hooked up to a quantum event. If the many worlds idea is right, the universe splits every time you pull the trigger. In a whole bunch of those branches, you die. But you can only continue to be conscious in the branches where you survive. From your own point of view, you would seem invincible.
So we have the pragmatists who say don't ask, the realists whose hopes were dashed by an experiment, and the radical idea of infinite parallel universes. After almost 100 years of this debate, has any team actually won the game? Well, here's where things stand today. The game is far from over. We now know for a fact that Einstein's common sense local version of reality is just not how the universe works. The old shut up and calculate approach is still the default for most working physicists. But those deeper questions haven't gone away, and mind-bending ideas like many worlds are still very much in the running. And all of this leaves us right back where we started, facing that central choice. This game of theories forces us to ask a really fundamental question about what we want from science in the first place. Is it good enough to just have a powerful tool that makes amazing predictions, or do we need it to give us a true, complete map of reality, no matter how profoundly strange that map turns out to be? The search for that answer is still very much on.